All right, we've already covered section 1, which was talking about what waves are, section 2, which is about what are the parts of the wave, and today we're going to discuss how waves behave, because they follow similar patterns in what we're doing, and so that kind of helps us to be able to figure out different things, to be able to decide what is going on and how they're actually interacting with each other. One of the first things that we're going to do is we're going to look at these essential questions. What is the law of reflection? Why do waves change direction when they travel from one material to another? How are refraction and diffraction similar and how are they different? And what happens when waves interfere with each other? On our vocabulary, we need to remember the words parallel and perpendicular, because that's going to be talking about the way and the direction of the force and the way the angles of everything work. Okay, so a perpendicular line, if you remember, is a line that forms a 90-degree angle with another line. So if our raindrop is falling down with that force, it's going to cause a transverse wave that moves at 90 degrees to the angle of the force to be perpendicular to the direction of the force. That's in comparison with the sound waves that are compression waves, because they move parallel to the direction of the force. So a parallel sound wave is going to, the force is going one way, and the force is moving the exact same way along the same plane. The new vocabulary that we're going to be covering today is refraction, diffraction, interference, standing wave, nodes, and resonance. Okay. These can be found in your book. One of the first things we're going to begin talking about is actually a reflection. You know what reflections are. You look at yourselves in the mirror all the time. I see many of you look in the reflection in the window. You see your reflection in your phone screens. You're looking at yourselves constantly. That visual reflection is one way that you see reflections. But sound echoing is also an example of a reflection. If you're in the quiet hallway and you close your locker, you can hear it echo. Those are all reflections. A reflection occurs when a wave strikes an object and bounces off of it. All types of waves, including sound, water, and light waves, can be reflected. So whenever you're looking at like a picture like this one, okay, light is hitting the girl. Okay, those light waves we don't necessarily see except for what they reflect off of. So that light, some of it is being absorbed into her skin and some of it is being reflected. That is the way we see different colors, we see different things, and we'll cover that more when we get to the chapter on light. But the light that bounces off of her is being reflected off of her. It is then going to the mirror, hitting that flat surface that is reflecting all of that light back to her eye. And then from that point, that is when your brain processes it. Similar things happen whenever you're hearing, sound. That sound has got to come and it's got to vibrate those vocal cords and it's got to travel to your ear. It vibrates your eardrum and that's how you hear that sound. And we'll get into that more as well later. But that's kind of what is going on, is that bouncing around of that light, and the way that happens affects the reflection. But if reflections work in a very specific way. If we think about it, if it hits a flat surface, okay, if a reflection is coming straight down and hitting a flat surface, it bounces straight back to that person. We understand that. We've seen that many, many times. That always happens. But what happens if you don't hit it straight on the actual line? So if you're not hitting perpendicular to the actual plane, what is actually happening with that light? It follows a rule. That rule is called the law of reflection. Okay, so if we take the line where our plane is, the mirror of sorts, and we draw a perpendicular line to that, that's the line that if that light was going straight down, that it would bounce exactly straight back up that same line. That is called the normal. That's perpendicular. If, by some chance, we are shining a light at an angle down to that plane, we can predict and we can know with certainty how that wave is going to react, because that normal line is going to create an angle. This is called the angle of incidence. Okay, this angle of incidence is from the normal to the light that's being shown. Okay, an incident, if you're reporting an incident, you're reporting what's actually happening. So from where the light is actually occurring to that line, you can measure that angle, and that is called the angle of incidence. On the other hand, if you go on the other side, that is going to be the reflection side. This is where the light is originating. That's the incident. It is being reflected on this side, and that is going to be the angle of reflection. Okay, because it's being reflected off this way. I can use the same angle that I used to find the angle of incidence, and I can mirror image it over on this side and find the exact angle of reflection. Because the law of reflection states that the angle of incidence is equal to the angle of reflection. If I make this line come up farther this way, if I take my light and make it further up this way, this one is going to be at a steeper angle. They are going to move the same exact way. They're going to move exactly the same direction. So, if I use this, I can take these and show you that that is the exact same angle here. If I increase one, it's going to increase the other because they are going to mirror image. If I increase if I make it wider, it's going to change that angle. They always follow that same thing. The same angle that I hit that plane to the normal, that angle of incidence, is going to be exactly the same angle as the angle of reflection. So it does not matter if it is at a 45-degree angle. If the angle of incidence is a 45-degree angle, the angle of reflection is going to be a 45-degree angle. If the angle of incidence is 18 degrees, the angle of reflection is also going to be 18 degrees. That kind of varies whenever we're going to be doing some different things now, because now we're going to move from reflection to refraction. You guys have all seen me do the thing where I put the straw in a glass of water. Whenever you have that straw in that glass of water, right there at that line, it looks like that straw is not attached. We know that that straw is attached. Our brains know that, but visually it looks like it is unattached. That is because that air, those light particles, are hitting two different mediums. If you remember, a medium is just the materials that we are moving through. So if I'm looking, my visual sight, the light that we're using, is traveling through air here. Air is spaced out, okay? And so that kind of goes through here. When it hits the water, those light beams are still going through the water, but it is a different medium. That water is more dense, and so those light waves are going to slow down as they go through that. Because they're going faster here and slower here, it makes those appear to bend. Reflection is where that light is actually bouncing off of an object. In refraction, refraction is the bending of a wave caused by a change in its speed as it travels from one medium, like the air, to another medium, like water. Anytime I'm making it go through different mediums, it is going to change the way it reflects. Because here I'm looking through only air, here I'm looking through air and water. Those are different mediums. They're going to bend the direction of that light. That applies the same way as I'm looking at things down here. I can use some of the same information that I used on the angle of reflection to be able to figure out what's going on here. The thickness of the liquid, or the different medium, is going to affect how it actually works. So if I used oil in here, or if I used glycerin, it would give a different angle of bend. So I can't use the angle of incidence here to be able to predict it. I just have to think and learn how different mediums react. But those light waves are going to hit that surface of the water, and then they're going to bend. Because what I'm actually looking at is going to, looks like it should be here, but it's not there. The same thing can happen if I go the opposite direction. So if I look down here at the bottom picture, if I shine my flashlight from the water, and it goes from the water, the thicker material, into the less dense material, it is actually going to speed up when it's here, and it's going to bend the other direction. And this was going to be going through thicker liquids into lighter, more dense into less dense, so it's going to be going slower into faster. The top one, remember, we were moving faster and then going slower. So just by changing the materials, either way we change materials, we are going to change the bend, the direction of that light. Okay, this is the reason why when you are fishing, bow fishing, you can't actually shoot the fish. Because when you're looking at fish in an area under the water, those fish are not really where they look like they are. That's the reason people have so much trouble trying to catch a fish in the water. It's because they look like they're in one area because your eyes are seeing the light go from an air into a liquid, and that light is bending. Those fish are not where they appear to be because that light is bending. Okay? Here's a good demonstration of that. Okay? If I'm looking from standing up on a pool at somebody standing in the water, okay, it looks like their feet are not really where they're at. He looks like his feet are right down here because that's where that light is bending. But his feet are actually up here. He appears to be taller than he is, and his waistline is going to look like it doesn't match, kind of like the way that straw does. That is the same principle behind a fish. A fish will actually be in this area when he appears to be here. So you're actually going to have to shoot up here in order to be able to hit the fish instead of down below it. That is covering reflection and refraction. The next thing is talking about how waves kind of bounce around some different things. Okay? The best way to explain this is thinking about a creek or a lake and thinking about how those waves actually bounce around. Because I don't know how well you can see this in the video, in this picture, but if you're looking at your books as you're doing this, you can see in this picture you've got all of these waves coming in from the ocean or from the lake, and they hit this island. You can see lots of waves hitting this island. Over here in this top corner, you can see those waves continue because they're not actually hitting anything. But you see all of this white where the waves are hitting that island. And then over here, you can see that there's not very many waves. It's very calm, very smooth. There's no waves kind of to this. Okay? But if you're looking really closely, you can see right in here, there's no waves here, and yet there's still a few waves beginning to happen here. That is because those waves are actually bending around this object. Because waves, as they're going out, are also spreading out. So when the wave comes past this area, it may be here, but then as it goes past, it goes a little bit bigger, and then a little bit bigger, and a little bit bigger, and a little bit bigger. It spreads out that energy. Kind of like a flashlight. When you're shining the light of a flashlight, it starts as a small beam and it gets wider as it goes out. All waves like to spread like this. So the diffraction is the bending of a wave around an object, like when a wave hits a shoreline, but then if you kind of go on past it, those waves will still start showing back up in that area. This picture may show it just a little better if you can kind of see it. I don't know how well you can see it on this book. It's not showing up real well. I'll try to make it a little bit darker on here. So if you look, there are straight waves coming through here. I think you can see that pretty good on the video. Then we have a solid object that's only allowing a small section to come through here. I am now going to mark these waves just a little darker. Hopefully you can see those. So those little waves are passing through here, but as they come through the hole, they're actually going to start bending, and they are getting larger as they come through. Okay. You can see that they are bending and stretching out. So even though this wave is not in this area, those waves are bending into that area. This is the same reason why on light waves we get the eclipse and we get the penumbra and the umbra, that very, very dark spot, and why even though we might be 99% covered, we still are getting some light, is because those light waves are bending around that area and we only have a small section that is completely dark because of that light bend, that diffraction around an object. We have lots of areas where we see that. That's the reason why we hear sounds as it bounces, it's bouncing around a corner or somebody is talking around a corner and not necessarily echoing. We also have that with radio waves and the way they interrupt with each other. And you can read about those more in your book, and that affects the wavelength. The last thing that we need to discuss is interference. Interference is when waves interact with each other. And there's a few different things that can happen, and hopefully you're going to be able to see some of that in a lab that you're going to do here before very long. If I have two people at opposite ends of a rope, and this person makes a really big wave on this side, and this person sends a really little wave this way, what's going to happen when they hit each other? Because they are going to combine and figure out what's going on. What's actually going to happen is a process called interference. It is a process of two or more waves overlapping and combining to form a new wave. That's right, they combine to make a new wave. This is a little wave. That little wave should continue to go this way. This big wave should continue to go this way. But as they hit, as the waves overlap, they interfere to form a new wave, and so that new wave is going to be in the middle and be the combination of both of those smaller waves. I know it sounds weird, but then after they interfere with each other, this little one is still going this way, this large one is still going this direction, and you're going to see that while they interfered and had that big one in the middle, as they continue moving, the little one moving this direction, the large one moving this way, they separate back out. Interference is when that kind of interferes in that one spot and causes that problem. This happens a lot with microphones. You have different wave patterns that are interfering with each other, and it's when you hear that loud, annoying, squeaky, squawky noise is when you have that interference. That's when those different wave patterns are interacting to create that new wave and that new sound that it's not supposed to be transmitting. So if we look over at this other section, okay, and we're looking at how these different waves, you can see that there is a wave 1 in the yellow and a wave 2 in the green. Okay, it can either create the one wave and then they both go back the direction that they did the way they were in that other example, or sometimes they behave in a way that creates an entirely new wave. So if I have wave 1 moving this direction and wave 2 moving this direction where they're counteracting each other, sometimes they will cause that big wave in the center to happen. Some other times they're actually going to combine. Okay, so I have a little wave that's moving here, a large wave that's moving here, and when they combine, they will actually create a new wave where their energies are actually interfering and bouncing off of each other. If I'm moving them both the same direction, it adds to the amplitude and they get bigger together. If they're moving opposite directions, they will actually counteract each other and make each other's waves smaller. It's the same principle as force. When two opposing forces are pushing on each other, okay, the one that is pushing the most will win, and it will move that direction. But if the forces are moving together, okay, then they add to each other. If they're moving apart, moving towards each other, then they will counteract each other, and the force won't, their resulting force won't be as strong. So this one, where they are actually working together, is called constructive interference. When you construct things, you're making things bigger and making them bigger. Destructive is when they're going to be tearing each other apart. They're going to be working against each other. That's what destruction is. That's going to help you to remember the difference between those two types of waves. Okay. we're going to work on standing waves and resonance on another one because this video is long enough, as well as nodes. So thank you.